Welcome to Heart of Mathematics. This is Euler's Characteristic and Algebraic Topology. So I noticed a lot of questions on the discussion board about how the definition of planar graphs fits in with drawing the graph on a torus. And this is, I believe, week 13's discussion board. So let's get an idea of what topology is. So topology is the study of how things in space are or are not the same under stretching, twisting, shrinking, bending, but not under cutting or gluing. So this is the idea of consistency under deformation. So this is like if we take a rubber band, we can twist it, stretch it, tweak it however we want. We just can't cut it or glue it back together. So for an example, if we have a squiggly line, no matter how much we squiggle it, this is consistently the same thing. I can stretch it around and I can smooth it out and I can get a circle. This is consistent. But this squiggly line here is not the same as if I had taken it and made two loops. That's not the same, assuming these two loops, this is drawn in the plane. Because here in the first example, I have a circle with one hole, and in the second example, I have two loops in this. It's almost as if I pinched it and glued it together. So we've got the example on the left as deformation, consistent deformation, and on the right, we've got the example of where we had glued two parts of the string together. So that's kind of easy to see on the plane, but when we start to look at dimensional objects, we can see our example of a sphere. Let me do this in a different color here. Our example of a sphere here, so we draw a circle, we give it a boundary on the outside, so you can kind of see this looks like a sphere. This is not the same as a torus or a donut. A donut we give kind of a little smiley face, and then a little thing like here. And the reason why this is not the same is because a sphere doesn't have a hole going through the center of it, but a donut does. And so we can talk about why these things aren't the same. We can't squish a sphere, no matter how hard we try, we can't squish a sphere into a donut without puncturing the sphere to get that donut shape, to get that hole in the center of the donut. So this leads to a question. Why can't a topologist tell the difference between a coffee cup and a donut? And so this is the idea of under deformation. So if we take a coffee cup here on the right, or excuse me, on the left, we see we've got the hole right here in the donut. So, or the hole in the coffee cup. So here is my little hole in my coffee cup. That's where the handle is. And that handle sticks through here as we go through. I'm marking it in red. So that handle becomes that hole in the donut. So I've carried that hole through. Now what happened to the body of the coffee cup where you put your coffee? Well, that shrinks down. So we have coffee cup, we have that full body, that lip there shrinks in. So that lip becomes smaller and smaller and smaller. And as it becomes smaller, it flattens in and flattens out. Hold on just a moment. Sorry, my dogs were barking at the mailman. So as that lip becomes smaller and smaller and smaller, it eventually disappears and becomes that edge of that donut here. So this edge is where that coffee cup lip used to be. So to a topologist, the coffee cup and the donut are actually the same thing. So a brief introduction to topology. So the question is how does algebraic topology, where algebraic topology is the idea of combining functions with one-to-one properties and onto properties, and we'll talk about this when we talk about Poincaré's conjecture, with graph theory. So how do we connect algebraic topology with graph theory? How do we deal with the idea that Euler's characteristic, where we had a formula for planar graphs, suddenly didn't work with K6, or rather K5, and one land, or K33 in one land. We had that agreement at the beginning of the semester. And then on a torus, suddenly it worked. Let's get some definitions down. So first, the genus of a surface. So the genus of a surface in algebraic topology land is what we describe as the number of holes, briefly speaking, in the surface. So if I have a sphere looks like a beach ball. That's a bad sphere. Let's try that drawing that sphere again. So sphere looks like a beach ball. So we call this, has no holes in it, so we call this S sub 0. So this has genus 0. So G equals 0. Has no holes in it, so it's genus 0. A torus has genus 1 because it has one hole in it. So we've got our little donut. So this is what we call S1. So our genus is a subscript on that one. We have a 2-hole torus, which would be if we took 2 donuts and smashed them together. So I have 2 donuts, and I give each of them a little hole. So this has got 2 holes, so this is S2. So this is genus 2. And we can continue on with this, but they don't have to look nice and pretty. I could look like a sphere, and I can just smash my donuts on top, like little ears. And then in red here, here's my little holes. So the majority of my sphere is completely fine. And now I've ended on 2 little handles. Sometimes topologists call these handles. It's still S2 because there's 2 handles, or 2 holes in the surface. So it still has genus equal to 2. It just looks slightly different than the normal representation of the 2-hole torus. But it's the same under deformation. So that's something to keep in mind. If you're looking at algebraic topology, sometimes things don't look the same, but you can squish it around to make it the same. So that's the algebraic topology definition. So the graph theorists are lazy. They use the same words. So the genus of a graph is the subscript of the first surface. So if we're looking at our surfaces above, S0, S1, S2, it's a subscript of the first surface on the family, S0, S1, S2, just like above, on which the graph can be drawn without edge crossings. And this is where the idea of planarity comes into play, without edge crossings. So without edge crossings, this gives us an idea of we can methodically search all of our surfaces up to some surface Sk to find the particular surface K, for its genus. So finding that particular number of holes that I need in order to draw my graph without edge crossings. So let's go back to our definition of planar. So graph is planar if it is drawn without edge crossings and it's drawn in a plane. This was our original definition of planar. The idea of genus, the genus of a graph, takes this definition and it generalizes the second point. So if we're generalizing this point, then we're allowing ourselves to have a little bit more flexibility. So instead of just saying, oh, it's got to be on a flat piece of paper, we say, well, if my flat piece of paper is got some holes in it, and I'm allowed to use the holes, then maybe my graph can live in a different land. So we're adding on kind of some dimensional aspects to this. So the set of all planar graphs, in planar that we understand planar, is equal to the set of all graphs with genus 0. And this is nice, because if I think about a sphere, if I take a sphere, here's my little sphere, a plane, any plane is just like I cut like a rectangle out of the sphere. This is my plane. So if I'm a planar graph with my original definition, so planar graph with my original definition, then it's equal to the set of all graphs with genus 0. So on my original plane, then I can draw on the sphere. So I can draw it on the sphere, I can cut it out and draw it on the plane. So this is an easy sort of thought process to prove. So when we're looking at the genus of a graph, so K4, we know that we can draw K4 on a sphere. But we can also, if we can draw K4 on a sphere, we can also draw on anything with holes. So let's draw K4 drawn on a torus. So K4, we know, has genus equal to 0 because it's planar. So we know we can draw it on a sphere. So if we draw it on a torus, we can either draw it just like we drew on K4, or rather on the sphere. So we can say, well, here's my planar graph. So here's my K4. So I can either draw it like that, not even use the hole, because I don't need the hole, because I could draw it just in the plane. Or I could use the hole. And we saw an example of this in one of the other videos. So I could say, given my K4, 1, 2, 3, 4, I could connect my K4, and I could wrap around one of the elements. Wrap this around here, and wrap this one around here. So I could use that hole, or I could not use that hole. It doesn't matter. But I know K4 has genus 0, so I could draw on everything that's got a larger genus. So K5, I can't draw on the sphere. We know K5 is not planar in the usual sense. So we can't draw, so we know if it's not planar in the usual sense, so its genus has to be greater than 0. So we can start taking our planar graph, or our torus. We can say, can we draw it on our torus? So we say, let's draw our little points here. So we have 1, 2, 3, 4, and 5. Let's connect our pentagon on the outside, and then connect some triangles here. And then we can connect around, I'm going to change colors here. You can connect around the top here. So this interior point here is connected to everything. It's connected to the 1, 2, 3, 4. So that one's taken care of. This point is connected to 1, 2, 3. It just needs to connect around here. So we can run this point all the way around the circle here. And then this point, 1, 2, we need to connect it to this guy. So here, let me change to a green pen. We need to connect this guy all the way down, and we loop it all the way around the circle. And so using that hole, we can connect K5 together without any edge crossings. So the genus of K5 is 1, because we only needed a torus, which has genus and algebraic topology of 1. So this is where the connection comes into play. So Euler's second formula says, well, vertices plus edges minus, or vertices plus faces minus edges is 2 minus 2g. Before, we just had the 2 as a piece for planar graphs. This minus 2g part is essentially minus 2 times the minimum number of handles needed to make that work. So if we need a handle, we have to add the genus to it. So this second part here, this is what we call the Euler characteristic. This is chi, the Greek letter chi. And so essentially, chi is 2 as our base value, minus 2 times the minimum number of handles needed to draw the graph. So G is the genus of the graph. You can say the genus of the graph or the genus of the surface. Because here, the surface, genus of the surface, and the genus of the graph represent each other. So I hope this clears up a little bit more of that. I'll be doing another video on Poincaré's conjecture, where we'll talk about homeomorphisms and some more pieces of topology and homotopies. So stay tuned.